and think about how it is you're going to be able to achieve that. Okay, so what work do you need to do in order to put yourself in the best possible position to walk away from school on Friday or from your computer on Friday and feel like you've achieved whatever it is you set out to achieve? So take some time to think about that. Take some time to start establishing some short-term goals that you can achieve before Friday at 2:45, and then start seeing yourself accomplishing those goals through hard work and through focus. Share my screen. So today, we're talking about unicellular organisms. Hopefully you've already started the warm-up, but this is Unit 2, Day 3, so I'm going to advance the timer to about 4 minutes. So 4 more minutes to knock out the warm-up, and then we'll jump into today's lesson about unicellular organisms.
Where do I find the warm-up at?
Yes, Michelle, you are new, so go into our Canvas page. Once you're in Canvas, the directions are basically right here. So once you're in our Canvas page, you're going to go to the modules section of the course, which is listed on the left side. There is a specific module for Unit 2. So you'll click into that module, and then you'll scroll down so you can find Day 3. And we've got a Unit 2, Day 3 warm-up. Okay. So as I said, if you didn't have time to complete the warm-up just now, you should have time later in class when we get to the asynchronous portion of the day, because this is going to be a pretty short lesson. But the objective for today is biologists will be able to explain how structures found within unicellular organisms help them to survive. The essential question that we will be hoping to answer at the end of the class is, why are adaptations required for unicellular organisms to survive? So this is the point in the lesson when you should have your notebooks out, whether your notebook is virtual or pen and paper or on your iPhone or your Android, whatever you choose, you should have some way of taking notes starting now. So the title of today's lesson is Unicellular Adaptations. And again, it is Unit 2, Day 3. So I see we've got a few more people who've joined. Sean, Kyrie.
I got a question. It might be a little random, but when are we going back to school like normal?
I don't think anybody knows that. That's a good question. I just don't think anybody has the answer right now. The last I heard is that the school is currently thinking of a plan to get the younger students in school first, meaning that'll probably be the elementary school students, and then high schoolers will probably be the last group to come back. So it'll probably, I really couldn't even put a timeline on it, but you'll know as soon as I do.
Yeah, all right. I just thought that, I don't know, I thought you knew, know something. I don't know.
Yeah, they're not telling us anything that they haven't told you all. All right, so I want to watch this video quickly because I think it just presents some interesting topics, but I also think it gives us some hope for the predicament that we are currently in with our own global pandemic. But this is about an older pandemic that affected human populations for a long time, killed many millions of people, and then it was eradicated. Oops.
10,000 years ago, a deadly virus arose in northeastern Africa. The virus spread through the air, attacking the skin cells, bone marrow, spleen, and lymph nodes of its victims. The unlucky infected developed fevers, vomiting, and rashes. 30% of infected people died during the second week of infection. Survivors bore scars and scabs for the rest of their lives. Smallpox had arrived. In 1350 BC, the first smallpox epidemics hit during the Egypt-Hittite War. Egyptian prisoners spread smallpox to the Hittites, which killed their king and devastated his civilization. Insidiously, smallpox made its way around the world via Egyptian merchants, then through the Arab world with the Crusades, and all the way to the Americas with the Spanish and Portuguese conquests. Since then, it has killed billions of people, with an estimated 300 to 500 million people killed in the 20th century alone. But smallpox is not unbeatable. In fact, the fall of smallpox started long before modern medicine. It began all the way back in 1022 AD. According to a small book called The Correct Treatment of Smallpox, a Buddhist nun living in a famous mountain named Ome Shan in the southern province of Sichuan would grind up smallpox scabs and blow the powder into nostrils of healthy people. She did this after noticing that those who managed to survive smallpox never got it again, and her odd treatment worked. The procedure, called variolation, slowly evolved, and by the 1700s, doctors were taking material from sores and putting them into healthy people through 4 or 5 scratches on the arm. This worked pretty well, as inoculated people would not get reinfected, but it wasn't foolproof. Up to 3% of people would still die after being exposed to the pus. It wasn't until English physician Edward Jenner noticed something interesting about dairy maids that we got our modern solution. At age 13, while Jenner was apprenticed to a country surgeon and apothecary in Sodbury, near Bristol, He heard a dairymaid say, "I shall never have smallpox, for I have had cowpox. I shall never have an ugly pockmarked face." Cowpox is a skin disease that resembles smallpox and infects cows. Later on, as a physician, he realized that she was right. Women who got cowpox didn't develop the deadly smallpox. Smallpox and cowpox viruses are from the same family, but when a virus infects an unfamiliar host, in this case cowpox infecting a human, it is less virulent. So Jenner decided to test whether the cowpox virus could be used to protect against smallpox. In May 1796, Jenner found a young dairymaid, Sarah Nelms, who had fresh cowpox lesions on her hand and arm, caught from the udders of a cow named Blossom. Using matter from her pustules, he inoculated James Phipps, the 8-year-old son of his gardener. After a few days of fever and discomfort, the boy seemed to recover. 2 months later, Jenner inoculated the boy again, this time with matter from a fresh smallpox lesion. No disease developed, and Jenner concluded that protection was complete. His plan had worked. Jenner later used the cowpox virus in several other people and challenged them repeatedly with smallpox, proving that they were immune to the disease. With this procedure, Jenner invented the smallpox vaccination. Unlike variolation, which used actual smallpox virus to try to protect people, vaccination used the far less dangerous cowpox virus. The medical establishment, cautious then as now, deliberated at length over his findings before accepting them. But eventually, vaccination was gradually accepted, and variolation became prohibited in England in 1840. After large vaccination campaigns throughout the 19th and 20th centuries, the World Health Organization certified smallpox's eradication in 1979. Jenner is forever remembered as the father of immunology. But let's not forget the dairymaid Sarah Nelms, Blossom the cow, and James Phipps, all heroes in this great adventure of vaccination, who helped eradicate smallpox.
All right, so I like that video because it, like I said, is somewhat hopeful to me, because what it illustrates is a global effort to eradicate a disease that killed, over the course of many thousands of years, it killed hundreds of millions of people. And so what they needed to do was work together in order to achieve a goal of eradicating this disease. And so we had many people from different cultures coming together, but one thing that they did not cover very well in the video is just how many cultures were affected and how many cultures played a role and how many different nations played a role in eradicating this disease. So they talked about the Chinese nun, the Buddhist nun, who perhaps was the first person, or maybe they were the first culture to use the practice of variolation, in which they took the scabs of people who had already been infected, they grinded those scabs down, and then they used those scabs to give a much weaker infection to another person. And that way, that person then developed an immunity to smallpox. But what they didn't talk about in the video is that very similar practices also existed in Africa at the exact same time. So we don't really know if that specific Chinese nun was the first person or if that was the first culture to develop that practice, because we do know that people in Western Africa were doing the same thing as they had been exposed to the virus as well. And those of you who might be history buffs, what do you know about the people from Western Africa? What happened to them in the 1500s and in the 1600s and 1700s? The Western African people in the 15, 16, 17, 1800s, what happened to them?
They didn't get diseases because they were slaves.
Okay, excellent. They were slaves. They were enslaved. So Europeans, once they arrived in the New World, needed to. They had a very large need for labor, and rather than paying the indigenous people or paying the African people to move to the Americas, they simply enslaved the African people. And the reason that they really didn't use the indigenous people as much is because the European people introduced diseases to the Americas. And in fact, smallpox, from the time that the Europeans arrived in 1492 until 1600, so only 108 years, in that time, the indigenous population decreased by 90%. So in 1492, there were about 60 million indigenous people living in the Americas. But by 1600, that population was only 6 million. So 54 million people died, primarily because of disease, but also because of war and genocide. And so there simply weren't enough of them. There weren't enough indigenous people in the Americas and what is today Mexico and Panama and Colombia and what we know now as South America and Latin America. There just weren't enough people left, and so they ended up enslaving Western Africans and bringing them to the Americas. Of course, the Western Africans were also subject to getting those same diseases, but what ended up happening is that they learned from the slaves, from the African slaves, that there was this process of variolation and that they had been doing it in Western Africa for a long time. They had been taking the scabs of people who had been infected by smallpox and using grinded up small amounts of those scabs to essentially infect other people, just to give them a small amount of disease so they could be immune. So they didn't talk about that in the video, but what we see is we've got people from Asian cultures, we've got people from African cultures, and we've got people from indigenous American cultures and European cultures all contributing to the understanding of this disease. In fact, the word vaccination, does any Spanish speakers in here, does anyone know how to say cow in Spanish? ¿Cómo se dice cow en español?
Vaca.
Vaca, and it's spelled V-A-C-A. So that's actually, vaca means cow in Spanish. And this is where we get the word vaccination, because the Spaniards were the first people really to widely use this cowpox vaccine to prevent smallpox. Okay, so even in the words that we use, we have all these different cultures contributing to something that is quite relevant today as we try to deal with our own global pandemic and develop a vaccine for today. So that video reminds me of the part that we all have to play, regardless of what culture we're a part of or where we live in the world, in eradicating this pandemic, because regardless of our geographic background or our ethnic background, we still have to be at least cognizant of the fact that anybody can get this disease. And so we're all taking our precautions to make sure that we're not endangering other people, but we also have all these different cultures and scientists and universities working to find this vaccine. And we've probably in the last 6 months learned more about the coronavirus than we have about most other viruses that have been in existence for a much longer period of time. And it's because we've worked together as a people, as a globe, to do this. So there's some inspiration to be taken from that. We still have a long way to go, but hopefully you all find some lesson in that video. I thought it was pretty cool. But in your notes, today we are talking about unicellular adaptations. Okay, so this is an important slide, and it's directly related to the essential question of the lesson. And what it says is multicellular organisms, like plants and animals, have organs and organ systems that help them perform essential life processes. So the essential life processes that we're talking about are Sternger. If you remember from our first week in the class when we were in Unit 0, it seems like a long time ago now, but The first week in the class, we talked about Sternger, which is an acronym which essentially spells out these 8 essential life processes. So multicellular organisms like plants and animals like you and I, we have all these different types of cells, we have different organs, we have different organ systems that are able to do different things for us that allow us to perform those 8 essential life processes. I have a digestive system that allows me to take in essential nutrients. That's the N in Sternger. I have specific cells that allow me to break down my food and then build up other things that my body needs. That's the synthesis. That's the S in Sternger. I have blood cells that carry oxygen and that carry waste away from my body through my blood. And that's the T, the transport. So we have these other specifications that allow us to do Sternger. But unicellular organisms don't have all those things because they're just made up of one cell. So they have to do everything with just one cell. They still have to do those essential life processes: synthesis, transport, excretion, regulation, nutrition, growth and development, respiration, and reproduction. They still have to do all 8 of those, but they can't rely on all different types of cells and organs to do it. They need to do all of them essentially internally. So they require what we call adaptations to survive. Looks like I've got some new people in here. Brian, happy birthday to you. Brian Castellan Avalos, happy birthday. Hope it's a great day for you. Hopefully you get a chance to enjoy yourself after school today. I appreciate you still being in class. Okay. All right, so the first adaptation that we'll talk about is called an eye spot. And it is essentially exactly what it sounds like. So obviously these unicellular organisms do not have literal eyes, but they do have this collection of proteins that can detect light. And this is what allows them to do photosynthesis. We're going to talk about photosynthesis much more in depth in about 2 units. But essentially, photosynthesis is the creation of energy, the creation of food using light, typically light from the sun. Okay, so this word phototaxis, if we break it down, we see photo in phototaxis and in photosynthesis. So that prefix photo, P-H-O-T-O, means light. So phototaxis, I need to now know what taxis, that suffix taxis means. Well, we could think of it like a taxi. It's something that moves. Taxis is movement. So, and I don't know if you guys know what taxis are. You only know Uber and Lyft, but taxis essentially were Uber and Lyft before Uber and Lyft. But phototaxis is movement in response to light. So some organisms like the light, and so they'll move towards it. And some of them don't like light, so they'll move away from it. And these eye spots are what allow the organisms to detect light. So here's a good video illustrating that. You're going to see the light turn on and see how it backs away. It doesn't like the light. Okay, so these eye spots are collections of proteins that allow organisms to detect light. They're essentially eyes, but they're very, 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 very rudimentary. No color, no depth, no shape. All you can tell is there light, yes or no? Then we have pseudopods. Pseudopods are temporary foot-like projections of the cytoplasm and cell membrane that allow an organism to grab and ingest food. Again, we can break this word down. Pseudo is a prefix meaning fake. And then pod is a suffix meaning foot. So a pseudopod is a fake foot. But this foot is not used for movement. This foot is used for digestion. Or ingestion, I should say. Taking in food. Okay. So here's a slow video of this. You'll see that these temporary projections are coming out of the cell. The cell is extending itself, and it's really in search of food. Now, in reality, this can often happen faster than what we're seeing right now, but they've probably placed, the cell in something that's pretty thick and sticky, so it just can't move that fast. All right. We also have cilia, C-I-L-I-A, and that is a plural word. Cilia are thousands of tiny hair-like structures surrounding a cell, allowing movement and the ability to sense the environment. So cilia are important not only for movement, but primarily so that the cell can know, okay, it's a little bit too cold over here. I need to go back to where I just came from. Or, okay, it's a little bit too salty over there. I need to back away from that. Or I like it right here. It's not too acidic, it's not too basic, so I'm just gonna try to stay here. So the cilia allow the organism to do regulation. Okay.
Many cells use flagella for moving around. These Chlamydomonas swim very fast using their two flagella. At higher magnification, the two flagella become visible when a cell is embedded in mucilage, slowing their activity right down. Like many algae, Chlamydomonas has an eye spot which responds to light and affects the way the flagella beat, steering the cell toward or away from it. Many protists have flagella of different length and function. This euglenoid, called Phacus, is swimming in the direction of its longer flagellum. These relatives of Phacus also have two flagella which function differently. One beats in a coil around the cell. The other, as in Phacus, extends forwards. Other algae have more than two flagella. This cell has 8, inserted into a deep pit. It normally swims very rapidly and had to be slowed down to have its picture taken. Large protists like Paramecium swim rapidly using hundreds or even thousands of flagella, or cilia as they are usually called. They are very agile as they search amongst the pond debris for food. Beating of the cilia is coordinated, and the direction of beating is reversed when the cell changes the direction it wants to go. This cell, like the last ones, had to be slowed down in a sticky solution so that it could be photographed. Many protists also use their cilia to create currents for feeding, carrying nearby organisms close enough to be eaten. These algae are too big for this protist, but show the currents clearly. This large protistan cell called stentor feeds like a vacuum cleaner. A circular array of cilia around the flattened end of the cell sucks nearby organisms into a conical mouth where it can check out what it has captured. It is feeding here on green algae. Notice that it is quite selective about what it eats, swallowing some of the captured cells and rejecting others. The cells of some tissues in animals have multiple cilia, like these cells cultured from lung tissue. The activity of the cilia is coordinated so that liquid or mucilage can be moved long distances over the surface of the tissue. Flagella and cilia contain a core of microtubules. Using polarized light for imaging the cells, the microtubules show up as a dark or light fiber inside each cilium.
Okay, here's another good image to show the cilia. You can see them moving on the outside of the cell. You can also see some other cellular features here. This is a mitochondria, this long thing. Here's a pseudopod sticking out. This is called a contractile vacuole, which we'll see in a couple of slides. A flagella, or several flagella, that's a plural word. Flagella are one or more whip-like structures that help to propel a cell through liquid. So oftentimes, as was discussed in that video that you just heard, an organism would have more than one flagella or flagellum. And the flagella are important because they allow for chemotaxis. So keep in mind that taxis is a root that means movement. Chemotaxis, therefore, is a word that means movement in response to a chemical environment. So some cells like a specific chemical environment. They like to be near zinc, or they like to be near in a combination of specific alcohols. Other cells like to avoid those same environments. And so they can sense those environments with their cilia, and then their flagella allow them to move away from those environments. In fact, this is actually how sperm cells are able to find egg cells, because egg cells have a specific chemical scent that egg cells are attracted to. And we'll see that in a video. I'll give you 10 more seconds to get down some stuff from this video.
Fertilization is the epic story of a single sperm facing incredible odds to unite with an egg and form a new human life. It is the story of all of us. During sexual intercourse, about 300 million sperm enter the vagina. Soon afterward, millions of them will either flow out of the vagina or die in its acidic environment. However, many survive because of the protective elements provided in the fluid surrounding them. Next, the sperm must pass through the cervix, an opening into the uterus. Usually, it remains tightly closed, but here the cervix is open for a few days while the woman ovulates. The sperm swim through the cervical mucus, which is thinned to a more watery consistency for easier passage. Once inside the cervix, the sperm continues swimming toward the uterus, though millions will die trying to make it through the mucus. Some sperm remain behind, caught in the folds of the cervix, but they may later continue the journey as a backup to the first group. Inside the uterus, muscular uterine contractions assist the sperm on their journey toward the egg. However, resident cells from the woman's immune system, mistaking the sperm for foreign invaders, destroy thousands more. Next, half the sperm head for the empty fallopian tube, while the other half swim toward the tube containing the unfertilized egg. Now, only a few thousand remain. Inside the fallopian tube, tiny cilia push the egg toward the uterus. To continue, the sperm must surge against this motion to reach the egg. Some sperm get trapped in the cilia and die. During this part of the journey, chemicals in the reproductive tract cause the membranes covering the heads of the sperm to change. As a result, the sperm become hyperactive, swimming harder and faster toward their destination. At long last, the sperm reach the egg. Only a few dozen of the original 300 million sperm remain. The egg is covered with a layer of cells called the corona radiata. The sperm must push through this layer to reach the outer layer of the egg, the zona pellucida. When sperm reach the zona pellucida, they attach to specialized sperm receptors on the surface, which triggers their acrosomes to release digestive enzymes, enabling the sperm to burrow into the layer. Inside the zona pellucida is a narrow, fluid-filled space just outside the egg cell membrane. The first sperm to make contact will fertilize the egg. After a perilous journey and against incredible odds, a single sperm attaches to the egg cell membrane. Within a few minutes, their outer membranes fuse and the egg pulls the sperm inside. This event causes changes in the egg membrane that prevent other sperm from attaching to it. Next, the egg releases chemicals that push other sperm away from the egg and create an impenetrable fertilization membrane. As the reaction spreads outward, the zona pellucida hardens, trapping any sperm unlucky enough to be caught inside. Outside the egg, sperm are no longer able to attach to the zona pellucida. Meanwhile, inside the egg, the tightly packed male genetic material spreads out. A new membrane forms around the genetic material, creating the male pronucleus. Inside, the genetic material reforms into 23 chromosomes. The female genetic material, awakened by the fusion of the sperm with the egg, finishes dividing, resulting in the female pronucleus, which also contains 23 chromosomes. As the male and female pronuclei form, spiderweb-like threads, called microtubules, pull them toward each other. The two sets of chromosomes join together, completing the process of fertilization. At this moment, a unique genetic code arises, instantly determining gender, hair color, eye color, and hundreds of other characteristics. This new single cell, the zygote, is the beginning of a new human being. And now the cilia and the fallopian tube gently sweep the zygote toward the uterus, where he or she will implant in the rich uterine lining, growing and maturing for the next 9 months until ready for birth.
Okay, so those processes we will talk about again at some point in the course and in greater detail as you all learn more about reproduction. But that was an introduction to sperm cells and also egg cells. But sperm cells rely specifically on flagella for movement. And lastly, our last adaptation is called a contractile vacuole. And this is a flexible contracting sac which stores and pumps out water. Water, of course, is needed for the creation of energy. We need water to make energy. All right. So here we can see a contractile vacuole that is going to pump out water. It's going to contract, and then when it contracts, it squeezes out water. And then we can see it grows to store water. So the cell has different needs, and at different times, it needs different amounts of water. We could also, we'll be able to see it again, but there's also a pseudopod that this organism projects from its cell membrane. Keep in mind the pseudopod is there in order to ingest food. There it is right there. You can see this pseudopod. Right. So, I forgot to do that. But this is a table maybe you will want to copy down. I was going to have you all answer these questions, but I forgot to block it out. But by revisiting the objective at the end of the lesson, I think we can get in the habit of just knowing what the takeaway should be. And so the objective was biologists will be able to explain how structures found within unicellular organisms help them to survive. So that means that we should be able to answer that question. How does it help unicellular organisms to survive? But here are the 5 adaptations, and then here's the function that they serve. Here's how they directly contribute to survival. So if you haven't written anything down, then this is probably what you should write down. This is what you should take a picture of. And then the essential question as well, we want to revisit that. Why are adaptations required for unicellular organisms to survive? So you should be able to answer that based on what you've learned today, based on what you've written in your notes. Why are they required for unicellular organisms to survive? And I want you to think back to the beginning of the lesson when I talked briefly about the difference between unicellular and multicellular organisms. So can someone take themselves off of mute and answer this question for us? Why are adaptations required for unicellular organisms to survive? No thoughts? Okay, so if you can, go ahead.
Because it helps them adjust to their surroundings, and it's how they produce. I mean, it's how they get food for nutrients, and like it's like how they maintain their body, basically.
Excellent. That's a great answer. So multicellular organisms, like I said at the beginning of the lesson, and Joseph touched on this too, multicellular organisms require different organs to survive. My brain does something different than my heart, which does something different than my biceps, which does something different than my stomach. So I have different organs and different organ systems for different functions. Unicellular organisms don't have all of those things. They're just one cell. So they need these adaptations to adapt to their environment. They need these adaptations to seek out food, to ingest food, to digest food. All right, so these adaptations, we can think about them as being similar in purpose to what our organs do for us. All right, so at this point, that's it for the synchronous portion. We've got 23 minutes for you all to knock out these assignments during the asynchronous portion of the class. You can find 2 assignments and an exit ticket on Canvas. They should be in that same place, Michelle. I know you're new, but if you still go into modules and then the Unit 2 module, there's a specific day that says Day 2, September 8th, 2020. And there you can find the exit ticket as well as these 2 assignments. One of them is about organelles, which we discussed last week. So if you maybe missed that lesson of organelles, it might be a better use of your time to watch Day 1's lesson, which was September 3rd. I will be on mute.
Mr. Rudd,
Yes.
can you put the picture up for question 8 on the exit ticket? Because I can't see it.
Okay, give me 1 second.
Okay, thank you.
Which exit ticket are you doing? Because today's exit ticket only has 6 questions.
I was on the one with 8 questions.
What day is it?
Unit 2.
Oh, you're not talking about the exit ticket. You're talking about the unicellular adaptations, or it should say adaptations practice.
Yeah, that's what I was talking about. My bad.
Okay, hold on. Give me 1 second. Oh, none of the pictures are showing up, are they?
No, sir.
Okay. All right. Well, don't worry about this assignment right now because it's going to take me a while to fix this.
Okay, yes, sir. I got you.
But thank you for bringing it to my attention.
Mr. Wright? Mr. Wright?
Yes. Yo, what's
Mr.
going on,
Wright?
Jaden?
That makeup addiction thing isn't working for me. That makeup addiction thing isn't working for me.
What's not working about it?
Like, it won't. Hold up. It's not letting me answer the question.
Yes.
You
So it's not letting you type in?
If you're not jumping on a trampoline, you need to come.
No, it's not.
Okay. I mean, it looks good on my end. I'm not sure. Have you tried to refresh your page?
Yeah.
Okay.
Yeah.
Okay. Well, why don't you share your screen with me? But I'm going to let everybody else go. It is 1:21 now, so you all are good to go. Thanks for being here today. Hopefully you took good notes. Hopefully you made progress on your assignments. And I hope you have a good rest of your Tuesday. I'll stop sharing my screen, Jaden, so you can share yours.
Never mind, Mr. Wright, it's working.
Okay.
I'm gonna do. You want me to I'm gonna do it.
Okay. I'll stop recording.